TLS as a cryptographic protocol is a protocol that runs on top of the transport protocol TCP. Probably lesser known is that with the Datagram Transport Layer Security Protocol DTLS, a derivative of TLS exists that runs on top of UDP. The latest DTLS version is version 1.3 and is based on TLS version 1.3. DTLS 1.3 aims to provide similar security guarantees as TLS 1.3, apart from order and loss protection of application data encapsulated. DTLS is not further discussed in this presentation, but to anyone interested in DTLS, the specification of the latest version, DTLS 1.3, can be found in RFC 9147. TLS is then used to encapsulate application layer protocols such as HTTP, FTP, or SMTP. If, for example, HTTP is encapsulated in TLS, this is referred to as HTTPS, having the quite famous IANA port number 443 assigned. With the discussion just had, and if we'd tried to fit TLS or DTLS as a communication protocol into a protocol model such as the TCP IP model, TLS or DTLS seem to fall in between the application layer and the transport layer. Clearly, the TCP IP model needs to be somewhat bent to embed TLS or DTLS. Trying to embed TLS or DTLS into the 7-layered OSI model, I happily leave as an exercise to my audience. A TLS connection between a client and a server essentially consists of 3 subprotocols. The connection starts with a handshake protocol initiated by the client, then proceeds into a protocol for the secure exchange of encapsulated application data, and when all application data was securely transmitted, the TLS connection proceeds into a protocol to close the connection. Of course, errors such as failing to agree on security parameters or failing to verify a certificate can happen at any time in each of the 3 subprotocol stages. As of TLS 1.3, all errors are considered fatal, and upon detection of an error, the detecting party sends an error message to its peer, with subsequently both parties closing the connection. From a cryptographic point of view, the by far most interesting TLS subprotocol is the initial handshake protocol. This handshake protocol is responsible for constructing the confidential and authentic channel between the client and the server. For this, the handshake protocol authenticates the peers involved in the connection and provides the means for the peers to agree on a master secret. Once a successful handshake finishes, the peers involved in the connection are authenticated and have agreed on a shared master secret. The application data exchanged later on between the peers is then symmetrically encrypted and authenticated with keys derived from the master secret. The color coding applied on the right side of this slide highlights that within TLS, 5 important cryptographic processes take place. The first of these processes, highlighted in green, is the cryptographic authentication of the peers involved in the connection. The second process, highlighted in blue, is the cryptographic agreement on a master secret. The third process, highlighted in yellow, is the symmetric encryption of application data. The fourth process, highlighted in pink, is the cryptographic authentication of application data, and the fifth process, highlighted in dark red, is the derivation of cryptographic keys from the initial master secret. This color coding I will apply consistently throughout this course, with the idea that this color coding may help to associate later, more detailed discussions of technical TLS features with the higher level cryptographic processes served. Clearly, TLS is a complex application of various cryptographic concepts, and interestingly, multiple combinations of cryptographic mechanisms and primitives can be used to achieve the overall objective of constructing a secure channel between a client and a server. The specification of which combination of cryptographic primitives and mechanisms to use is given by what TLS calls cipher suites, and it's such a cipher suite that a client and server will have to agree on essentially first thing within the handshake. How the agreement on a cipher suite really works, we will get to see in a following lesson.